Hi there, my name is Mason Cole, and today I'll be going over the description of motion for the Mars rover helicopter problem that we were assigned for this group project, along with my group partners, Benjamin and Colin, who will be covering the other topics later on. All right, so for the description of motion, we were stated in the problem that when the motion of the helicopter starts at little t equals negative of capital T. So I describe this in two different forms in terms of the x direction and in terms of the y direction, since uh, if you think about it in a real world context, a helicopter will be moving up and forward or backward at the same time as well. So it makes sense that it moves in the x direction as well as the y direction. So as you can see here on the slide in front of you, I say, or we say that the helicopter accelerates in the x plus directions from little t is greater than negative t. And then at t equals 0, the acceleration begins to change and increases in the negative direction indefinitely. In terms of displacement from the origin from when the helicopter first took off, the motion would be going forward first, stopping at some point, and then going towards the negative direction indefinitely. And then to compound that in terms of the y direction, at little t equals negative capital T, acceleration is in the positive y direction, which would be moving the helicopter upward from its initial position. And then from t equals 0 to little t equals capital T, the velocity is in the positive direction. And then once little t becomes greater than or equal to capital T, the velocity will then be in the negative direction. In terms of the y-axis on the helicopter for the motion, the helicopter would move up before stopping at some point in the air, once again rising again, and then stopping one more time before it finally started to descend and come down. When talking about both the x and y direction, we can infer that the helicopter will reach the ground after the helicopter changes its direction and is going in the negative x direction. And that basically sums up the description of motion. I'll be handing off the video to one of my other group mates to describe or for the sense making portion of this problem. Thanks.
So we are given that the new rover helicopter has an acceleration of the vector formula at a of t, which we are trying to find an equation to find its final position. We need to integrate. And to integrate a vector, we need to integrate each x and y separate and not to integrate them together due to them being two separate equations. We will integrate around little t and treat all other values as constants. The constants will be big T, beta, and alpha. Once we do the integration, we get the velocity formula that is shown below the acceleration formula. When we integrate into the velocity, we need to remember to bring in a v initial in both x and y. The v initial takes the place of a plus c that we would normally put in when we integrate. Now we put big T back into the velocity formula to find out what v initial in the x and y, which comes out to in the x beta times big T times little t over 2 and 0 in the y. With that, we can now integrate again to find the position formula. The position formula will not have a initial position due to the fact we are more concerned with a change in position and will go away when we look for delta position. Now we have a position formula we need to find out change in both x and y, since the initial t, little t equals negative big T, and the final time equals positive big T. We will just use the final and times it by 2 when we get to the step to get both of the sides. So we put a big T in to both equations and times both of them by 2, and the change in x will also give us the distance, or d. Now we can solve for big T using the equations. We use the change in x equation to find big T because it had a distance and got T squared equals 3D over 2 beta. Then had to square root to our equation of big T equals the square root of 3D over 2 beta. Big T gives us how much time the helicopter rover is in the air. Then plug in the D into the change in Y to get our final equation for the distance in the Y direction, which is the alpha over 35 beta times D. This slide is a representation of our acceleration graph, velocity, and position. Position is set at initial at 0 due to we can change it at any time and it will give us the same looking graph. It'll just change it on the y-intercept. Since alpha and beta are constants, we assume that they're greater than or equal to 0. And with T final equals big T and little t initial equals the negative T, the helicopter's position is dependent on what the time, big T, which is time in air, is, while alpha and beta are constant. For the units of this will be in meters or feet for the position.
So this is the reflection from our group. So we covered, a couple problems related to the rover problem. One of these is the Mario problem, which is the first equation on there from week 2. So this problem has, a handful of similarities. One of those is that it's, starting with an acceleration equation, just like the rover problem. Another one is that it has T over capital T, so being, time over time period, which is not something that you see in, every equation. So seeing it in these couple equations is somewhat unique. And then it also deals with acceleration in the x direction using, an x vector. But that also is one of the big differences, is that, the Martian rover problem deals with acceleration in both the x and y direction, whereas the Mario problem is only dealing with x. For the second problem, the bike and stoplight problem from homework 2, which is the second equation on there, it also has some similarities with the time over time period and acceleration or velocity in the y direction. But that's also one of the big differences, is that the starting equation is velocity, and it's also only dealing with acceleration in one direction instead of both. But then third problem that is also related is all of the arrow problems we covered in the studio. Because they both deal, they all deal with shooting an arrow and finding the X and Y position and velocity and everything. And that shows up in the rover problem. And then difference is that they don't really cover time over time period, whereas the rover problem does.